So the topic of today's class is a continuation of the ring model that we discussed last week, and before we go on discussing the math, I would like to bring to your attention a very interesting and exciting paper that came out exactly I think 1 or 2 years ago in Nature, about something like a ring in the fly. Yes. I'm sorry? Anyone interested in taking notes?
Yeah, and is it possible to do careful saying for people that did it once can do it again? Because we do want to do it, but it takes lots of time.
אני אשמח לסכם היום, השיעור מוקלט.
כן.
בעזרת השם.
כולם הוקלטו עד עכשיו.
אוקיי, כפל מבצעים זה לשאול את איתמר. בסדר? Okay, so before describing this paper, I'd like to say a few words about the history. So the ring model was introduced in the 1990s to account for some interesting results in the representation of orientation in the primary visual cortex. Mainly something that is called contrast invariance, that I don't want to go too much into, but the main idea or the main issue was that there were issues about the fact that the sensitivity seemed to be independent of the contrast, something that one would expect from something like the bump solution that we discussed. The mathematical idea, so the ring model was introduced to explain orientation selectivity in the primary visual cortex.
What do you mean when you say that sensitivity was dependent from the contrast?
So, as I said, I don't want to go into the details because then I have to explain what contrast is and show you some more experimental results, something that I don't want to do. But a result, the mathematical result of the bump solution that we discussed is that properties of the bump in the presence of weak external input, the pattern of activity in the network is almost independent of the, it depends on the orientation of the stimulus, but not on the magnitude or the strength of the stimulus. And this was something that people tried to explain. The ideas behind the ring model, the idea of something like a amplification of unstable modes, this is something that I think the first one to discuss was Alan Turing in the I can't remember if it was 1940s or 1950s. He had a very nice paper on morphogenesis. Now, I'm sure all of you heard about Alan Turing and his contributions to computer science, but he also had a very interesting paper, a very original paper addressing the question of how something like an oocyte that is symmetric gives rise to a body that has broken symmetry in it. Like we have limbs, so something is broken in the development of the embryo, and he asked the question, what are the mechanisms, and had a model for spontaneous symmetry breaking. Now these ideas are known as Turing instability, and the ring model was building on this Turing instability and proposing a way of breaking symmetry in the cortex.
What do you mean by unstable mode? I mean, in our
Well, the homogeneous solution was unstable. So, and the stable solution had broken symmetry, and we had a continuum of such stable, non-homogeneous solutions. Now, in your everyday life, you also find this symmetry breaking. An example, if you fry something, okay? So you hit the pan and then you put oil, and then something which may not be very wise to do, but still, if you look from above on the pan, you see that the oil is not symmetrically distributed. So there are like patterns. So this is an example where everything is homogeneous, where the heat, if your pan is good enough, then the heat is more or less homogeneous, but you still get a spatial pattern.
And related to the shape of the pan or the heat conditions?
So the question is what will determine this pattern. So it could be either noise or it could be the boundary conditions of the pan. So this is an example where you have a physical process that is homogeneous, but the solution is heterogeneous. So this is another example of Turing instability, and there are many such examples. So this ring model is just another example of something like Turing instability, and I think it's interesting that an idea that was proposed, a mathematical idea that was brought forward to explain morphogenesis, turned out to be of relevance to a model of the cortex. And now, 2 years ago, there was this paper that I want to tell you a little bit about, which was about orientation in a fly. Now, flies, as you all know, don't have a cortex, but still, they looked at orientation selectivity in the fly, and the idea is the following: you put a fly on this ball made of foam. There's air coming from below, so there's very little friction, and the fly is in the presence of something like virtual reality. These are the stimuli. While the fly is moving around, these are transgenic flies, and with calcium indicators. So one can look at the neural activity in a brain region that is known as the ellipsoid body, which is here. And well, as you could have imagined from the name, the ellipsoid body has a shape of an ellipse, right? And so the experiment looks something like this. You have neurons here that have calcium indicators. This is a fly. This is a 2-photon laser scanning microscope, enabling the researchers to measure activity for the concentration of calcium, and they do it in this virtual reality environment. And this is how it looks. So this is the fly on the ball. It's moving around. This is a stimulus presented to the fly, moving around. And this is activity, pattern of activity in the ellipsoid body. And this is analysis of one of these is the location of the stimulus, and the other is the location as extracted from the population activity in the ellipsoid body. And you see that there is a bump of activity that seems to follow the external stimulus.
What do you mean by bump?
Well, whenever so if of course I'm not very precise, but you should be used to it by now. So now I'm looking at the population activity. So this would be these would be the neurons along the ellipsoid body, and for if the animal is presented with stimulus of one orientation, say this orientation, this is the pattern of activity you see in the network. And if the animal is presented with another stimulus, this would be the pattern of activity in the network. So if you look at the entire network, you see some elevated activity which corresponds to the location of the stimulus.
How do you extract from this red line?
Well, I don't remember the details, but the way that this would be typically done, you find the preferred or preferred direction of each neuron, and you look at the strength of activity as you'll do it I'm sure you'll do it next year, but the idea is that you define a vector R which is equal to sum over I AR AI RI, where AI is a coefficient that corresponds to the current activity of the neuron, and RI is the preferred direction. So, and this is what you measure, the direction of this vector. Yes?
Did they measure the orientation, the rotation of the ball itself, to see if it's correlated with the...
We'll soon. More questions?
What did you say? AI? RI?
This is the instantaneous level of activity, in this case measured by...
What we want, how will be the result?
This would be the population, the direction encoded by the population.
Vector of the direction.
Yeah. Okay. So, but still, I mean, maybe these neurons just correspond to, I don't know, to just reflect the external activity. The external stimulus are just, I mean, maybe this is like the retina of the fly. So this is another experiment. This time the pattern is very different. Okay, the pattern is very different. The visual pattern is very different. But still, what you see in the neural activity is that the population response tracks the orientation and doesn't care about the details of the stimulus. So these neurons really care about orientation.
Orientation what?
Orientation of this stimulus.
What's
Like in
different orientation?
Well, you can define, for example, the center. Let's see, soon we will see one. We will perhaps address your question in a second, but when you can think about the center of this as a direction, and then look at the activity. So the neural activity is not qualitatively different from what we saw previously, despite the fact that the stimulus itself is very different. These neurons don't, the activity of these neurons don't reflect the details of the visual stimulus, they only reflect the direction of this visual stimulus.
So what happens, part of the stimulus is multidirectional, from two directions.
No, there's one object that is moving. So there's one visual object here. So the neurons care about the direction of this visual object. They don't care about the details. So it just moves. So this is a ring. So things move from here to the other side. Okay. The boundary conditions here are periodic.
It's not relative. It's absolute. Like it's not relative to the. Do the fly sense the movement of the stimuli, or does it actually know where it is exactly? Like, do you understand my question? I don't know.
Yeah, it's a direction. The direction itself.
How do they show it's not just the respective fields of the...
Because this is not different from I'm sorry, this is not different from this. So the visual stimulus is very different, but the response is not.
So it's just the parts that
No, it supported its direction rather than the reflection of the detailed visual stimulus. If it would have been, maybe this example would be better, but here they show two bars. Okay, so if what these neurons reflect is the details of the visual stimulus, then you would have expected to see two bumps of activity. If it is just a direction of a visual object, or visual environment, something global, then you would expect to see one bump.
Couldn't it also be water?
I'm sorry?
Couldn't it also be water? No kind of water?
No, because that's you mean a reflection of the response of the animal to the visual stimulus. I don't remember how they control for that. So these are two bars, and again you see one bump of activity. Reflecting the idea is that these neurons encode a global measure. Again, I did not control for your issue, which is a motor response, a global measure. Actually, it's much nicer on my computer. You can. I mean, this paper is available. You can just download and look at it. It's very nice. Now, what's not one thing that is nice about it? Just a second is, as I told you many times, that the ring model does not imply that neurons reside on a ring, right? This was like a virtual ring. Well, here it's really a ring. Okay, it's really, these neurons really reside on a ring. Someone had a question here?
Yeah, I don't understand if what you said coding is direction of movement or place in the visual state.
The direction of the direction of the animal relative to a visual stimulus. So
Of which part of the
maybe I'll show you another one, another movie. Perhaps it will address it. Okay, so now I will show you the activity in this region when the animal is in the dark. So there's no visual stimulus.
But it can walk on the wall.
Yes, it still walks on the wall.
Do you fix the editor?
I'm sorry?
How is it? I mean, is it fixed to that ball or it can fly?
No. It cannot fly. I think that the way that it's fixed is, you see it here.
One more.
Yeah, it's glued to this rod, okay? And you do imaging, but it still can move its legs. And you can change the environment in accordance with its motion. And this is what's done here. This is in the dark. Animal is moving. So you can look at the bump of activity. Well, I don't know if it's in response to its motion, but the idea is that what these neurons encode is a direction of the animal in space.
Like head direction?
Like exactly, it's like head direction, but in the fly.
What are they blinking?
What are the blinking? I don't know.
But if the animal is head, why would you see?
But it's transparent.
What? No,
Why would
they
the electrical activity happen?
no. You do use
They
use calcium indicators. I don't know what these blinkings are.
So what does it matter? I mean, if it's head direction or something like that, what does it matter what the stimulus is? Or
Well, it's
that
head
it's
direction.
orientation or
Well,
something?
when you even when in all animals, if you talk about head direction relative to something.
It's not relative to yourself?
No. This is relative to the world. Head direction relative to the world. So this is an example of a system that seems consistent with the ring model. So there are several issues here. One is, well, there are many issues, and Vivek and his friends are currently studying the mechanisms and the connectivity to see whether it is indeed consistent with what's expected from the ring model. I don't think that they have any results yet, but this is an interesting question, perhaps a place where the ring model can be put to an experimental test. One thing another thing that is interesting to think about in the framework of this experiment is how does, so let's say that we accept the ring framework and there is a bump of activity. How does external input change the location of the bump? So this is very similar to the question that we asked regarding integration in the framework of working memory. Now the bump resides on a manifold. It's like a line attractor. So it can, assuming that everything is symmetrical, the bump can be in any location, in this case along this ellipsoid body, and it's interesting to think how inputs to the ellipsoid body are integrated, resulting in motion of the bump. So this is one way in which the bump can move as a result of external input. Questions?
I mean, we show that the bump arises when there is no, the input is homogeneous.
So
Here,
I'm sorry?
here is the input here is
Here it's homogeneous. There's no input. Still you get a bump. Yes?
So how do you reconcile this with, perception? I assume
With perception?
yeah, the size of the So when is it the bump no perception? And
Well, you have a perception of where you are in space, even when you close your eyes.
But they can do the same effect.
But this is relative to an object, right?
Not when there's no, not when you turn off the light, not when you turn off the visual stimulus.
Why do you need this?
Why do you need this? Well, that's one reason why you may, well, first, if a fly flies in the dark, you may want to know the direction in which it flies, or temporarily flies in the dark.
Do you just guess, or is it kind of memory?
No, it's not memory. It integrates all the information that it has. So it starts from a particular location, then it integrates its motion as is seen here. So obviously it doesn't make much sense if you don't have any information about the world at all. But if you have partial information about the world, then it's worthwhile knowing where you are in space, and what's the direction in which you are in space.
But what's the regularity, I mean, in this behavior? I mean, I don't see the difference between this behavior and just the guess. I mean,
Well, it's
what
not a
makes
guess.
it efficient?
External input resets. In the presence of external input, the external input resets the location. But if there is a temporary gap in the sensory information, it can integrate its motion to determine its location, even in the absence of external input. Okay, so
I'm not sure how this integration relates to what we talked about in the bump.
well, what we talked about in the bump is the fact that a bump exists, and that there's a continuum of locations in which the bump can reside, similar to the working memory. So the same idea that we discussed in the framework of working memory and integration also apply here. Now, as I said, I'm not going to discuss now how external inputs are integrated to generate the motion of the bump, but still you can imagine that such a thing exists. Similar to the conceptually similar to the integration in the case of putting them away. For example, something, yeah. More questions?
Why did the non-homogeneous fixed point that we got from last time stable? Because it's still J1 is larger than 2, according to the equations.
So so J2 has two components. It amplifies nearby neurons, but it kills other neurons, so it turns them to 0. So I'm not sure that I understand your question.
We talked about the homogeneous solution, and we showed that it's unstable. And it was unstable because of the parameter J1 that was larger than 2. And I don't see how it changes when we move to the other solution that is non.
So one way of thinking about this, perhaps, is looking at this equation. So when J1 is very large, in order for this to be equal to 1, theta c has to be small. So fewer and fewer neurons are active, but those active are very active. Since there are very few neurons that are active, then the total amount of input is relatively small. As a result, the pattern of activity is the overall activity is finite. Now, when this is about existence. Now, when you talk about stability, that's a more complicated issue. So all these solutions are marginally stable, because if you have a bump solution like this, you'll also have a bump solution like this. So the stability is marginal in the direction of.
So what makes it stable?
So again, it's not exactly stable; it's marginally stable.
And how?
In the direction of in this direction, it is marginally stable. Now, one way of seeing it, even without doing the calculation, is realizing that you have a continuum of solutions. So if you have a continuum of fixed points, then each fixed point has to be marginally stable, or at least in the direction of the continuum of fixed points, it has to be marginal. Now, you can ask a question about stability in the direction that is orthogonal to this direction. There it's more complicated, but you'll have to take my word for it. Okay? More questions? Okay, so now we will, for the fun of it, we will consider the case of a ring model with connectivity that is not symmetric. What are the consequences of adding asymmetric connectivity? Now, this is from a theoretical point of view, this is pretty horrible, because now there's no guarantee for an existence of a fixed point, right? Because we can only prove that the dynamics will converge to a fixed point in the case of symmetric connections.
In the case of the symmetric connection, why do you know that there's a fixed point and not that the system diverges?
We proved a theorem like a month ago that any network with this was using the energy function. Remember? So this would prove it. So everything will be the same as before, but we will consider a different connectivity matrix. J of theta will be equal to J0. This is a homogeneous component. Plus J1 cosine of theta. This is the symmetric component as before. Plus epsilon J1 sine of theta. So this is the new addition. And we will consider the untuned case. So there is no selectivity in the external input. We will consider the case of J1 that is larger than 2 and J0 that is smaller than 1. This is the regime in which we have a bump solution. Actually, we will assume that in the absence of epsilon there is a bump solution. And we will assume that this term is relatively small. Okay?
What is this term again?
This is the asymmetry that we add to the connectivity. We will assume that it's small. Why are we assuming that it is small? Sorry? Why? Well, because this is something that we can. Because this is something that we can easily solve. That's the reason. We're considering a problem that is relatively easy to solve. So let's write the equations. So the equations are as before. Tau ds dt is equal to minus s plus threshold nonlinearity of h, where h of theta and t is equal to integral from minus pi to pi d theta prime over 2 pi j theta minus theta prime s theta prime and t plus the external input I0 theta minus theta 0. Okay, that's as similar as before. External input will be constant. So we are done again. We wrote down the model. So from here on, it's only math. Questions? But before going into solving it, we'll try to gain some intuition about the behavior. So we already know how the model will behave when epsilon is equal to 0, right? How will it behave? What will be the structure solution? Without an external input, yes. There will be a bump. Well, So this bump will look something like this. So this would be, let me try and draw a bump. So this would be, this is the expected solution in the absence of asymmetry. This would be the case of epsilon being equal to 0.
What are the theorems for that?
I'm sorry? Well, this would be theta. This would be a neural number or theta. And this would be activity, F something, S. This should have been S, right? Activity. So this is a solution. This is a solution in the case of epsilon being equal to 0. And now we're trying to gain some insight into what will happen if we take epsilon that is not equal to 0 but very small. So we'll start from here. Let's look at the input. Let's try and figure it out from the input. So, well, we have this homogeneous term, which is easy and we don't care about. We should all the interesting things come from this term. Now this term has two components. I'm sorry? So this term has two components where there is a same component as before, d theta prime over 2 pi, j0 plus j1 cosine of theta minus theta prime plus epsilon j1 sine of theta minus theta prime times s of theta prime in t. Right, this is an interesting part of the equation, and we already know how to solve this part, or we already know what the contribution of this part, j0 plus j1 cosine plus the external input. This would give us this bump solution. Now let's try and understand what will be the contribution of this term. What will be the contribution of this term to the bump? So remember, this function corresponds to the activity of different neurons. So let's choose a neuron, a random neuron. Let's consider this neuron. Okay, a neuron that is here. Let's consider the neuron that is here whose activity has this value. So this particular neuron, we will think about this particular neuron. So this neuron, we'll consider this one. So this one is theta. What will be the contribution of this term to the activity of this particular neuron?
Minus the output contribution to that cosine.
Well, not exactly. No, cosine is not minus cosine, right?
To reduce the activity.
I'm sorry?
To reduce the activity.
Why will it reduce the activity?
Because sine, when theta is negative, sine is negative.
Okay, so let's consider this term. So basically, this neuron receives input from all other neurons in the network, modulated by this term. We don't care about this term because this term is the one responsible for this level of activity. So we only care about this term. So we need to integrate over all neurons in the network with this weight. Some neurons in the network has a positive, has a larger angle than this one. These would be neurons in this direction. Some will, will be larger and some will be smaller. Now, let's consider the ones that have a larger angle. For these, sine of theta minus theta prime is negative. So these neurons will contribute a negative. These neurons will contribute a negative net input to this neuron. Whereas these neurons on the left-hand side will contribute a positive net input, because this term is positive. So the net contribution of this term will be a sum of the positive terms and the negative terms. I'm sorry, sum of input coming from neurons whose angle is larger, whose contribution will be negative, and neurons whose angle is smaller, whose contribution is larger. Now, if you look, there are many more neurons on the right-hand side of this one, and fewer neurons on the left-hand side of this one.
Well, 0 and 2 pi, where does it correspond on this graph? Is it the beginning of the bump and the end of the bump, or?
Well, we don't know. The location of the bump is arbitrary, so we can choose to put it wherever we want. I'm just looking at neurons relative to this one. So there are neurons whose angle is larger. Again, if this one would be 2 pi minus delta, then 2 pi plus delta would be larger. To the right of this one and to the left of this one. And if you look, you note that there are more neurons to the right than to the left, and the ones to the right have a higher firing rate. Because there are neurons to the left, but their firing rate, most of them, their firing rate is 0. Whereas there are many neurons to the right who has a firing rate that is substantially larger than 0. So we expect that the net contribution of this term would be to reduce the firing of this one. So we expect that the firing of this one, change colors, we expect that the firing rate of this one will go down. What will happen to a neuron here? The firing will go up. So we expect that this term, what it will do, it will bring down the firing rate of all these neurons, not only this one, but also this one and this one. All these will go down. And all these will go up. Okay, so if all these go down and all these go up, how will the bump look like? Well, it will be shifted. Something like this, right? So this. I'm sorry?
Not all of them will distort.
Okay, so there will be two issues. One, it will distort, but we expect that this one will go up and this one will go down. Okay.
Yeah, because the center is staying like it is. Not necessarily.
Well, once these ones go down and these ones go up, what will happen to these ones?
No, so the center is on top.
Well, okay, so we understood that this should go down and this should go up. And maybe there will be also a distortion. Okay, but now let's consider the new bump of activity. What can we say about the new bump of activity? What will be the contribution of, what will be the, so now all neurons receive a new input. But still these neurons receive more negative input than these ones that receive more positive input. So what will happen to the bump? Well, it will shift to the right. And this will happen again and again and again. So the net effect of this term would be what? There will be a traveling wave. There will be a traveling bump of activity, if you like, that you will move right. And since the boundary conditions are periodic, what we expect to see in time, so this is our ring, there will be a bump of activity that will move Yeah, that will move. Basically, we expect to see a periodic solution.
Isn't the middle neuron supposed to be the same?
Initially, they are the same. But once those go down and those go up, then the middle neurons, the input to the middle neuron is no longer symmetric. Yes?
So to observe this shift, to observe this traveling, I have to solve the equation more than once, right? Because once I solve it...
Well, kind of. It's more complicated than that, because this is a differential equation. So there's no point looking at... the way that I described it is in discrete time. So I said, okay, let's see what will happen after some time, assuming that nothing changes, and we concluded that this will go down, this will go up, and then we'll have a new bump, and then we stop, and then we solve it again. So, but we cannot really do it this way because it's a differential equation. We have to use continuous time, and this we will solve it after the break.
Will occur according to the time passing, or is it like?
Yeah.
Yeah.
So the solution would be a bump that is moving periodically around the ring. Yes.
If you got distortion, it will keep accumulating and will ruin your bump eventually.
I'm sorry?
But the distortion you get will accumulate over time.
Well, it will accumulate, but there will be a new bump that will be formed. We will see. We will solve it analytically. Don't worry. We'll do it right after the break. Questions? It will be a limit cycle, but not not the boring, simple limit cycle that you were studying in the course of Tohar. It will be an interesting limit cycle in principle the number of neurons here is infinite. So it's kind of the limit cycle that we were discussing with Tohar were ones where the dimensionality of the differential equations was finite. I don't know, let's say 2, I guess. There were 2 variables. Here you have a continuum of variables. So this makes the problem more fun. Okay, we'll take 15. We will convene at 1:05.
טוב, פה שם מה לראות שזה טראבלינג ווייב בגלל שהכל פונקציה מינוס נטס או משהו כזה ואז ברור לך שזה סינק נכון שהוא מתרצה להבין את ממש למבנה של ההפרעה אבל זה ממש עם הפרעה אחרת לא דווקא היא מקבל טראבלינג הפרעה שהיא לא סינק נגיד?
קודם כל אני לא חושב שזה כזה טריוויאלי לראות את זה כל הפרעה בעצם כל הפרעה, מה שיש כאן, זה שיש כאן, שוב, יש כאן משהו שנשמר בסימטריה של הבעיה, ולכן הפתרון היחיד שאפשר לחשוב עליו כאן זה traveling wave. אם היית מכניס הפרעה לקוסינוס, נגיד, זה היה משנה פשוט את הצורה של הבאמפ, אבל היה נשאר סטציונרי. שבירת הסימטריה, פה יש לך שבירת סימטריה בלי זה, שבירת סימטריה שדיברנו עליה, שבירת סימטריה מרחבית. יותר ה-Turing instability הקלאסי. כאן יש לך שבירת סימטריה שהיא spatial temporal. יש לך שבירת סימטריה גם מרחבית וגם זמנית, זה קוראים פאזה שזזה. זה הדבר הסימטרי כאן מכניס לשבירת סימטריה, ואז שוב הפתרון הסימטרי היחיד שנשאר זה משהו שהוא traveling wave, אבל שהפאזה היא ארביטררית.
אם זה לא היה סינוס זה היה משהו אחר?
מה זה משהו אחר?
קבוע. אני יודע, כן.
קבוע לא יעשה כלום.
נכון, קבוע לא.
צריך משהו שתלוי בטסה.
כן, זה
ליניארי בטסה.
כל
ליניארי
פונקציה.
בטסה, כן.
לא, רגע, אם היית מכניס משהו שהוא... יש כאן 2 שבירות של... כאן, מה שאתם עושים, מה שהשבירה הזאת עושה, היא עדיין שומרת על כל האלמנטים של הבעיה, הם נראים אותו דבר. המבנה הוא אותו מבנה. אין כאן זוויות מועדפות.
זה מה שאומר על זה מחזורים.
כן, אין כאן זוויות מועדפות. זה לא מספיק שזה מחזור, אין כאן זוויות מועדפות. כולם בעצם רואים את אותו מבנה של קונקטיביטי. רק בהינתן אקטיביטי יש לך שבירת סימטריה. ולכן הפתרון היחיד האפשרי הוא traveling wave המהירות גבוהה. עכשיו, אם היית מכניס משהו שהיה שובר את הסימטריה לטרנסלציה מבחינת הקישוריות, אז היית מקבל תופעה שנקראת פינינג. זה סביר שהיית נתקע בבאמפ במקום מסוים. בגלל שסוג מסוים של סימטריה נשמר פה, והפתרון היחיד הוא traveling wave. כן.
מה אני מחזיק עכשיו להיות קצת אחורה? אני בשיעור הקודם, אני חורק קצת הסיכומים שלו.
אוקיי.
לא יודע, על משהו להבין שם. על נוגע לנקודת פיקס פוינט הלא ההטרוגנית.
ההטרוגנית.
כאילו חקרנו בהתחלה נקודה באופן כללי את המערכת, בלי שהתחלנו לחפש פיקס פוינט. כן התחלנו לחפש פיקס פוינט, לא החלטנו אם הן הומוגניות או הטרוגניות. ואז קיבלנו משוואות עבור A0, A1, A2, נכון?
A3, A4, A5.
כן, כן, אבל כל אלה הם לא מעניינות, כולם שם דוחות. A0, A1, A2 כאילו...
ו-B1, כן.
כן, ו-B1. ואז ראינו שבשביל פיקס פוינט כולם שם חייבות להתאפס, נכון? A0 דוט חייב להתאפס, A1 דוט חייב להתאפס, ו-B1 דוט חייב להתאפס. נכון? זה כהגדרה לפיקס פוינט כלשהי.
לא, לפיקס פוינט הומוגני. רק
להומוגני? זהו, זה מה שלא הבנתי, כי בסיכום כתוב שזה תכונה של פיקס פוינט, לפני שבכלל התחלנו לדבר על הומוגני.
זה פיקס פוינט הומוגני.
למה? אז איך זה יכול להיות שיהיה פיקס פוינט שה-A1 דוט שלו לא יהיה 0?
לא אחד דוט, A1 יהיה שונה.
לא A1 דוט, אני מדבר על A1 דוט.
בוודאי, לא, A1 דוט.
אבל זהו, אבל המשוואה של A1 דוט היא בסוף A1 דוט שווה A1 כפול משהו. בהנחה שאין לו איזה אינפוט, נכון? אז אם A1 דוט שווה 0, אז גם A1 שווה 0.
לא, כי יש לך A1. יש לך, היה שם איבר של I1.
אבל אותו חיפשנו במקרה הזה. אז זהו, אז אנחנו הנחנו שהאינפוט הוא הומוגני, כלומר A1 שווה 0. אבל איכשהו עדיין הגענו לנקודה הזאת שבה אתה אומר A1 לא שווה 0. כאילו בכל מקרה הזה...
בסדר, כן. מה שאם תשים לב, כשבנינו את הפיקס פוינט האלה, עברנו דרך ההנחה ש-H היא לינארית.
נכון.
זה לא מתקיים, ההנחה הזאת נשברת.
בגלל ש-H לא לינארית, אז אנחנו יכולים להגיד שזה משהו אחר, שאנחנו לא יודעים מה, ואנחנו
לא.
מניחים את זה?
הפוך.
איך זה מסתדר עם המשוואה של A1 דוט שווה?
המשוואה הזאת נכונה
רק במקרה הלינארי.
רק במקרה הלינארי. עכשיו, אם אתה מניח פיקס פוינט הומוגני, אתה יכול להראות ש-H ו-I0 הוא חיובי, אז H הוא ברג'ים הלינארי לכולם. ואז המשוואה הזאת תקיים. אבל זה כבר לא נכון, כאשר בכן אתה רואה שזה לא נכון, בזה שיש לך חטא C. חטא C אומר שיש לך חלק מהנוירונים שהם האינפוט של המוצר.
לא הגעתי עוד חטא C, אבל כן. אבל אני אגיע לשם, זה רציתי קודם להבין.
העובדה שלא כל הנוירונים...
שיש איזו קפיצה בנגזרת?
שתמיד הפעילות היא קוסיין עד לנקודה מסוימת ו-0, כשהקוסיין יהיה שלילי.
זה בגלל האי-לינארי.
זה בגלל האי-לינארי, ואז כל החישובים שעשינו הם לא נכונים.
הבנתי, ולכן הבאמפ הזה הוא לא רציף בנגזרת.
זו שאלה טובה, שאלה טובה. התשובה שלא הבהרתי את זה בצורה יותר טובה.
אני חושב שאני תשאל את המשהו של רגע. אז לגבי הרג'ים שבו יש לנו Amplification, J0 קטן 1, J2 קטן 2, J1 J1 קטן 2. במקרה הזה, אם האינפוט הוא הומוגני, האם אני אקבל פתרון הומוגני? כי נראה לך שלא. גם ברג'ים של Amplification, שבו אין לי J1 גדול משתנה.
כן.
האם שם, אם האינפוט יהיה הומוגני, האם אני אקבל פתרון הומוגני? גם שם נראה שאני אקבל באמפ, נכון?
לא. שם הפיקס פוינט הומוגני הוא יציב.
אני גם לא מבין משהו זה פונדמנטלי, אז A1 יכול להיות 0? כלומר, רואים שאני כן?
A1 0, פתרון הומוגני.
המשוואה הדינמית של A1 דוט.
כן, שווה למינוס A1 ועוד, מה זה J1 חצי 2 A1
ועוד ב-A1 0, אני מקבל ערך חיובי, נכון? זה לא ערך... נכון? זה כך נראה.
לא, תראי A1 שווה 0. זאת אומרת, המשוואה, אבל משהו כמו...
אבל כל הזמן ב-A1.
A1 דוט שווה למינוס A1 ועוד J1 חצי 2 A1 ועוד I1 0, יכול להיות?
הייתי ב-1 0.
רגע, ואם I1, לא, אם I1 הוא 0.
כן, תודה.
זה לא טריוויאלי הבאמפ הזה, אני יודע. ה-ring model הוא ככה, הוא מבלבל, אבל הוא מעניין.
כן, שאלה כזאת. כשאמרו לה באמפ, אמרנו שזה איזשהו מצב שבו האפליקציה שלנו היא לא תלויה באפליקציה שלה, בתלות בוקר. כאילו שהפרעה קטנה יכולה להפוך לאפליקציה מאוד גדולה. אפשר להוריד את
את הסלקטיביות כמה שאנחנו רוצים, אנחנו עדיין נקבל איזושהי מוטיבציה מאוד גדולה.
כן.
אז כשאתה מצייר את זה, אוקיי, כשהראית ככה את הבאונד סטייט, למה זה מראה את מה שאמרנו עכשיו? כאילו, נגיד, זה הרי משהו שיכול להיות גם במצב שלו באונד סטייט, הצורה הזאת שלה. הצורה הזאת יכולה לתרום גם בסאונד פתאום.
אני עכשיו מדבר על מקרה של אינפוט F, של האינפוט הטרוגני 0, זאת אומרת אינפוט הומוגני.
זה היה 1-0 כאילו?
בפעם אתה מקבל אותו רק במקרה של... מקבל את זה רק שזה יחד גדול מ-2.
כן, כן, זה אני מבין, אני שואל איך הגרף הזה של F כפול פשוטת היה נראה שונה אם זה לא היה פעם. אתה לשם? אבל יש לנו גם רג'ים של אמפליפיקיישן, כמו שזה...
אמפליפיקיישן, אבל אם I1
I1 לא יהיה שווה. זה החלק איפה.
בסדר?
תודה.
נראה לי שהיא גרם לנו להסתפר בטקס, באמת, כאילו, זה לא כזה זמן, הם כזה, לא מתחילים מתי זה, זה ואז כאילו הם צריכים לזוז דברים, זה, כמו זה, זה לא כזה, זה היה פשוט
Okay, so we are discussing the case of the ring model with asymmetric connectivity. In the case in which the unperturbed connectivity, the solution would be a bump. And we were wondering what would be the consequences of adding connectivity which is asymmetric. Thinking hard about this problem, we already know the answer. We already know that the answer would be that the solution would be periodic, that we will have a bump that is moving around this ring. Now, so there are, I guess, two questions that are left. One is what would be the speed of this bump, and the second question is what would be the shape of the bump. So I don't remember who brought this up, but this adding this perturbation to the connectivity can have two effects. First, the bump would be moving, and second, the shape of the bump may change. Right? Yes?
But you told the movement is according to the time. We don't see the exact, how do you say it? For a shot. The explicit function of the time here. So
here.
Yeah, so in this solution, we cannot see it. We have to solve it.
Well, eventually we'll have to solve it, but you already know the answer, so it makes your life easier. You know that the answer would be a rotating bump. What else can there be? But the only thing is what is the speed and what's the shape. So let's start with the speed. What would be the speed? I mean, it's much easier to do calculations if you know the answer. So it's worthwhile thinking about things before doing the math. Because in this case, the math is kind of unpleasant. Not very unpleasant, but slightly unpleasant. Something that has to do with tau. Thank you very much.
And epsilon.
And epsilon. Well, what do we know? We know that we expect that if we double tau, then the speed would go down by a factor of 2. Well, we know that speed is distance divided by time. And we know that the speed would be 0 if epsilon is equal to 0. So there should be tau there, and there should be epsilon there. Epsilon should be in the numerator, and tau should be in the denominator. And the only thing that may worry us is the question of whether there will be 2 pi there, or square root of 2 pi, or maybe e, or something like that. But other than that, it should be something like epsilon over tau. Right? So we know quite a lot without working hard.
We don't know what function of epsilon.
I want it to be complex.
Okay, what function of epsilon? That's the question. What function? Could be epsilon square. Could be. But unlikely.
Why?
Why? Well, in general, there will be some, let's call it velocity or something. Velocity will be some function, I need a letter, G? Did we use G?
Yes.
So not G, not H,
M.
V, okay?
No.
Should be some function of epsilon. And after a long and tedious calculation, we will find this V. And then we will Taylor expand V and take the first term in the Taylor expansion, and there's no reason to think why there will not be a first order term in the Taylor expansion. Well, the zeros term we already know. When epsilon is equal to 0, this will be equal to 0. So we expect it to be linear in epsilon. Maybe we'll I mean, this is expectation, not a proof or anything. So there'll be a linear term. So maybe it will be epsilon over tau, maybe it will be 2 pi epsilon over tau, maybe it will be 1 over 2 pi epsilon over tau, something like that. This is what we expect. Right? And so this is one thing. And second is something about the shape of this bump. Now, I guess we don't care much about the shape because, well, there will be a correction of the order of epsilon to the shape, which may lead to a correction of epsilon squared in the velocity or something like that. The main effect, if we will do some measurements, will be a change, will be the fact that the bump will start moving, and there will be something about the velocity. So the main thing that we care about is the velocity. So how are we going to prove? How are we going to find all these things? So the way to do it is use the fact that we already know the answer, which is nice. So first, we're looking for a solution. Let's write it here. So there will be something that will move, right? And the something that will move will have we know what the shape will be when epsilon is equal to 0, because we already calculated. So in principle, there could be a correction to the shape. But the correction, again, using the same argument as before, there would be the zeros term, the bump, plus corrections, which would be order epsilon. And if epsilon is small, then there could be corrections to the shape. But the main effect would be the fact that the bump is no longer stationary, but is moving. Well, if it will be wider, then maybe it will be order epsilon wider.
But it will accumulate in time.
No, because we're looking for a periodic solution. So one thing that you could argue is maybe the whole perturbation, this whole expansion analysis is wrong, and there will be something that will be qualitatively different in the case of adding this perturbation. This could be. Right. Okay, we can. If there will be a moving something that will be there will be a moving bump, that we know that it will be in some sense wider, because this bump solution is a asymptotic solution, a stationary solution. So this zero, in order for this to be zero, this will decay exponentially to zero, exponentially fast. But still, you need to wait an infinite amount of time in order to reach the solution. So if you have something that is moving, then you will not have enough time to go to, well, you will not have an infinite amount of time to reach zero. So the solution will no longer look exactly like the bump, but could be close to it, to the original bump. Do you follow?
Like it would affect the function of the network.
I'm sorry? Will it affect the function of the network? This is something that is in a different domain.
Activity, not the qualitative.
The point that I'm trying to make is that there will be changes to the solution, but they will be of the order of epsilon. That's what we expect. Okay. So since we're looking for a solution that is periodic, then rather than thinking about the activity of a neuron theta at time t, we can assume that it is some function of theta minus wt. So rather than thinking about two independent variables, angle and time, this periodic solution that we're looking at, we will guess a solution that has this shape. It's a function of the theta minus wt. So it's like a rotating phase. Questions?
Maybe very basic. How can you see this periodic?
Well, this was our intuitive analysis.
I'm just what you will now.
How is it periodic? Well, when wt is equal to 2 pi, or 4 pi, or 6 pi, you get exactly the same solution. And when w... Okay?
What's the definition of S?
You assume that S is 2 pi.
Well, S is defined only on the ring. Furthermore, I'm going to assume that S is the unperturbed bump. So we already know the shape of the bump. We already know something about the shape of the bump in the case of epsilon being equal to 0. So I'm going to assume that this is I'm going to assume that this periodic function looks like the bump, but in a moving coordinates framework.
The shape is the same.
The shape is so. I will be more. One should be careful here. So I'm going to argue that if I write this set of if I write this equation, this partial differential equation, or if we think about discrete space, this set of differential equations, and I consider only perturbations up to epsilon, then S is, I can consider the unperturbed bump as a solution. Well, there are two things. One is that you have a shape, the same thing that is moving. This is one thing, and this has to be. And if the solution is periodic, there's no other way because of the symmetry here. But second thing, this is a stronger assumption that it's the same bump that we computed previously. Now, with this assumption, I'm going to plug these two assumptions into my set of equations. I'm going to solve them, and to show that indeed this is a fixed point. In the rotating coordinates framework, this is a fixed point, and I'm going to find the W. Questions? Everything is clear? Okay, so let's write the equations. From here on, it's all very simple. Tau ds dt let's already save some time and write h of theta and t is equal to integral d theta prime over 2 pi j0 plus j1 cosine of theta minus theta prime plus epsilon j1 sine of theta minus theta prime s theta prime dt. So I'm just wrote down this term plus the external. We need to add the external input. Which is constant for all. Yes. Now I'm going to move to rotating coordinates. Why am I going to change rotating coordinates? What do I gain? Then this is constant. Everything is constant. Right. Okay. So this would be equal to d theta prime prime over 2 pi j0 plus j1 cosine of theta minus theta prime prime minus wt plus epsilon j1 sine of theta minus theta prime prime minus wt times s theta prime prime plus this external input.
Shouldn't it be not omega t?
No.
No.
No. Theta prime is equal to theta prime plus omega t.
But this is exactly the point where I'm always confused about when solving this. Okay, so this is a painful question. Well, theta prime is equal to theta prime prime plus wt, and here you had minus. Okay. Okay, but from here on, it's kind of straightforward, right? Because we have this term and this term. It's a cosine of theta prime prime plus something, and sine of theta prime prime plus something.
You need to change the boundaries also.
Minus pi to pi.
Okay.
Okay. So I can open it up, and then I have something like cosine of theta prime prime and sine of theta prime prime integral over s theta prime prime, which will give me the Fourier coefficient of theta prime prime, which is the A0 that we had previously. A1, I'm sorry, that we had previously, yes?
Where's the S theta prime constant?
Because we, in the rotating set of coordinates, it's constant. So W will be, will determine, we are considering W to be exactly the W of the speed of rotation, which we still don't know, but we will calculate. If you change the coordinate at the speed of the rotating bump, then it's stationary. So I'm assuming that the bump is stationary, but I don't know the speed. I'm moving together with the bump, at the speed of the bump.
I understand intuitively, but I'm not sure how it is in a slide.
Well, we will do it now. Okay, so we have cosine of theta minus WT minus theta prime prime is equal to cosine of theta minus WT cosine of theta prime prime plus sine of theta minus WT sine theta prime prime, and we have sine of theta minus WT minus theta prime prime is equal to sine theta minus WT cosine theta prime prime minus cosine of theta minus WT sine theta prime prime. Okay. Let's do this integral. Let's be bold and do it in one step. Okay, so we have h of theta and t is equal to integral d theta prime prime over 2 pi of j0 s theta prime prime is equal to this term, the first one, j0 times s theta prime prime integral d theta prime prime over 2 pi. j0 a0 over 2. Right? That's the zeros term. And we have the I00, let's put it together. This one. So we are done with this one, and we are done with the J0. Plus, so far so good, J1. We are good with J1. Okay, we have this term. What can we say about this term? So this term has two components. We have this term, and we have this term. So we have cosine theta minus WT. We don't integrate over it. So I can just put it here. Cosine of theta minus wt. I'm just looking at the first term. Times a1 over 2. Times a1 over 2. So this is the first term. This term. What about the second term? So the second term will contribute sine of theta minus wt. b1 over 2. How much is b1 over 2? If we consider s to be, we're looking, we're here, we're assuming that theta 0, if you like, the location of the bump is at 0. 0. Because the bump is symmetric, so this term will not contribute anything. Again, it's an integral of a symmetric and an asymmetric and antisymmetric, it's called antisymmetric function. Symmetric, antisymmetric. Okay, we are good. We are halfway through. Well, not half. We just finished this one. But now we have this one. But it's easy. Second one is easy. Plus, that was easy. Epsilon was easy. J1 easy. Okay, we have this term. This term, well, we have two components. Let's look at the second one first. 0. Okay, so let's look at this one.
a1 over 2.
So this would be just equal to sine theta minus wt times a1 over 2. Good. Not so bad, right? Because it's the same bump as before, yes. Okay, so the original equation, let's write it again, is tau s dot is equal to minus s plus g of h, where g was the threshold linear, but I would rather I'd rather leave it as g for the time being. Okay. So now let's consider the right-hand side of the equation, this term.
G is the nonlinear.
This is a nonlinear. So I'm going to consider the right-hand side of the equation. So this would be equal to minus s theta minus wt. So we assume again that the solution is a rotating bump. Plus g No, this is like capital S, yes. plus g. So let's look at this term. We already know it. Well, you don't see it, right? You cannot see anything here. Or can you?
No.
Okay. So what can we say about this term? What can you say? Well, this is a bump solution. Almost shifted, rotated bump solution. So this I will call it H0 theta minus WT. There is plus this term plus epsilon J1 A1 over 2 sine of theta minus WT, where H0 of theta minus WT is just equal to J0 A0 over 2 plus I00 plus J1 A1 over 2 cosine of theta minus WT. Okay. What's the value of G of H0?
G is the threshold value.
Yes, but what can we say about G of H0? It's exactly the bump. It's exactly equal to S. Well, we don't have G of H0. We have G of H0 plus something small. So what can we do? Expand, Taylor expansion. Okay. So going back to the right-hand side of the equation, this would be equal to minus S, this capital S, plus G of H0 theta minus WT, plus G prime of H0 theta minus WT times epsilon J1 A1 over 2 sine of theta minus WT. Questions? Well, I Taylor expanded the function G around H0. And the reason that I did it, well, because this term is equal to this term. I'm so happy. You should also be happy. One day you will be happy. So the right-hand side of the equation is just equal to G prime H0 theta minus WT times epsilon J1 A1 over 2 sine of theta minus WT. Okay. Questions? Other questions? We're all happy? Okay. So now we can discuss the left-hand side of the equation. So we are interested in tau and again we will assume this moving bump solution. So we can write it as the derivative with respect to theta minus wt of this s times d dt of theta minus wt. Equal to tau, the derivative of s times minus w. Now, since s of theta minus wt is equal to g of h0 theta minus wt, then this term is just equal to this term. The derivative of theta minus wt is just equal to g prime h0 of theta minus wt.
Multiplied by minus w tau.
Minus w. No, taking the derivative with respect to theta minus wt. I'm sorry. Yeah, with the
You should keep the w in tau on the left hand side.
I have to.
This term is also with respect to theta minus omega t. So it's okay.
Missing the A1 Ken, that's what I'm missing. The derivative of
שורה אחרונה.
Yeah, we need to add the derivative of h0 with respect to theta minus wt, which will give me times minus j1 a1 over 2 sine of theta minus wt. That's right. Okay? I'm taking derivative with respect to theta minus wt. I had to take the derivative of h0 theta minus wt. So I have the derivative here. I'm left with the minus j1 a1 over 2 sine theta minus wt, which is exactly this term. Okay. After this stressful break, so we know that the right-hand side of the equation is equal to the left-hand side of the equation. So let's see. So we will have here the minus with a minus. So the left-hand side will give us omega tau, or w tau, g prime of h0 times j1 a1 over 2 sine of theta minus wt is equal to it should be equal to g prime of h0 times epsilon times j1 a1 over 2 sine of theta minus wt, which implies that w is equal to epsilon over tau, as we expected all along. Now, so the whole point of doing this exercise, well, there were several things. One was, obviously, it was fun, and this was, I think, a first example to many of you of how to use this method of perturbation in order to in this case, compute the velocity of the bump and see how the asymmetric connections give rise to a moving bump. Questions? Some of you may be interested about the higher order terms. Where do they enter? Well, in principle, we took only, when we Taylor expanded, we took only first order terms. So in principle, you'll have higher order terms that will affect there will be a first order effect on the shape of the bump, order epsilon, which will result in an epsilon square effect on the velocity, which in turn will result in an epsilon square change to the shape, which will result in an epsilon cube effect on the velocity, and so on and so forth. So, but if we're only interested in the first order term, then this is dominated by the original shape of the bump, and we don't care about corrections, the order epsilon corrections to the bump. Questions? that's a very good point to end, because on Thursday we will start talking about associative memory. Associative memory, עקרון אסוציאטיבי. וכאלה.